So today, we're going to talk about bivariate data analysis. Bi means two. Variate refers to continuous quantitative variable. By two, this refers to quantitative variables like age and blood pressure. They're quantitative, right? So comparing two quantitative variables, look at this now. Some examples, BP and BMI. Is it quantitative or qualitative? BMI.
Quantity.
BP,
Quantity.
what are quantity? So it's bivariate. What about this two?
Quantity.
Quantity. What about this two?
Quantity.
Quantity. So the objective is you want to see how these two variables are associated. For example, is it true higher the BMI, higher the BP? Is it true higher the expenditure, lower the savings? Is it true higher the temperature in New York, higher the rainfall in KL? We don't know how it works. So these are bivariate analysis. There are three steps. The first step is scatter plots. You're going to plot the two variables, one on the x-axis, one on the y-axis. Right. When you plot it, it can be like figure 1, figure 2, or figure 3. How do you explain figure 1?
Positive correlation.
Positive correlation. Besides that, don't use any statistical term. In a common language, layman language, how do you explain this? Layman's language.
Related.
Layman's language. The higher the value on x, the higher value on y, right?
Yes.
Problem number 2.
Higher the y and
Higher
higher
the value on x. Always take the x first.
Lower the y.
Yeah.
Yeah.
As your x increase, y also increase. As x increase, y decrease. How about here?
No.
There's no association. So these two, we say there is association. How does it work?
Association.
Higher the x, higher the y, higher the x, lower the y. All right. So that's purpose of scatter plot, to see visually how the variables are interconnected. Maybe this can be like your figure 1, isn't it? Correct? Number 1, BMI as BP. Higher BMI, higher BP.
Yes.
Maybe it's like number 1. Number 2, is it possible more you spend, less you save?
Yeah.
Possible?
No.
Huh? More you spend, expenditure, more you spend, less you save?
Yes.
All right, possible? Then it'll be like this.
Okay.
Temperature in New York, rainfall in KL, are they connected?
No.
Maybe not. Then the figure may look like this. So visualize first. Look at the pattern first. That's scatter plot. Next, how do you describe these two? 1 and 2.
The higher x and the
Higher
higher y.
Higher y. What about here?
Still, but not close to 1. Not 100%.
But still,
I mean,
similar pattern, right?
Still,
Higher,
still have
right? What's
Yes.
the difference?
Similar.
Now we can see these dots are very close, right? This
Yes.
far apart, right?
yes.
So this is looks like strong. This is a bit weak, right?
Yes.
Not strong.
Not strong. So for that, we do correlation. How strong the association? Number 1, very strong. Number 2, not so strong, right? So the correlation value ranges from -1 to +1, center 0. With +1, perfect association. We don't see in practice. -1, perfect negative, and we don't see in practice either. Very close to zero, that means like this. Temperature and rainfall in New York and KL. Imagine this, we are going up the lift. The lift has fixed space, height. Every time the lift stops, you go certain height from the floor. We don't need analysis. This, imagine coming down the lift is coming down, every floor stops, it goes fixed distance down. We don't need this. So we are interested in this area and in this area. Positive is strong to 1 or strong to 0. Negative, is it very strong, close to 1, -1, or close to 0? So generally, values within plus or minus 0.3 are considered small. It's called from the Cohen's criterion. Any values within 0.3 and 0. minus 0.3, consider small. As the value of the green increases, you can say strong association, positive, strong association, negative. So to interpret this now, our description same, higher the X, higher the Y, higher the X, higher the Y. But what's the difference? This is all a compact, this will be loose. So this must be strong, this must be a bit less. The strength must be a bit lower. So you measure correlation now. That value is 0.976. This value is 0.659. Both are positive, but this is much more stronger than this. When you're comparing two data sets, this determines, because they're comparable, this is much stronger compared to this. So besides looking at the plot, you must also look at these values. And that is correlation. Next, regression. If you see a pattern, we say higher the value in X, higher value in Y. I want to know, and this increase, how much Y increases. Now we draw a line, the best line that fit the data. So in this line, we can measure the slope. As an increase, X increase delta, how much Y increases. So ratio between these two is called the slope. So normally we set delta X as 1. Then you're asking, every unit increase in X, how much Y increases? So that's called the slope. The equation, y equals to a plus bx. The b is the slope, how it's measured. A is intercept, where this line will cut the y-axis. So we're not so much interested in this, we are interested in the slope. So in regression, you're going to check whether slope is it 0 or not 0. Slope 0 means the line will go straight like this, flat line. Slope is 0. If the slope not 0, that means the line will be slanting, going up this way. Positive slope, it comes down this way, is a negative slope. So the regression is going to test that the line, this gradient of the line, 0 or not 0. Now, the distances, all the dots here, look at the dots, they're not sitting exactly on the line. So this space from here to here, distance, is called residual. So what's residual? Observed, which is the red points, red dots, and predicted. For this, what is the predicted value on the line? On the line. So these are called residuals. Regression analysis or assumption on the residuals. So you must understand what's residual, right? These residuals, they have some assumptions. So say every test, there are assumptions. So we know what's residual. So residuals can be positive if above the line, negative below the line. We take the sum of the residuals, answer will be 0. Plus, minus cancel out. So what do you do? We square the distances. We square them. And then take the sum. So now, this residual is bigger the better, smaller the better?
Smaller.
Smaller the better. So what does it do? You fit many lines and take the line that gives the smallest residual. Hence, the method is called OLS, ordinary least square. Of what? Of the residuals. So that's called the best line. The best line is the one that gives the lowest sum. So now the assumption on the residual is that there are many assumptions on this. Just 2 assumptions: must be independent and normally distributed. So again, test the normality going to come again and again in many tests. So this collection of the residuals first must be independent, they don't connect to each other, and distributed normally. So how do you test this? First assumption, independent. We plot predicted versus residual. That is, we plot the values on the dot, values on the line, values on the line versus the differences. You're going to plot this. Don't worry, SPSS plots for you. The plot, if the assumption is met, assumption independent, these dots must be random like this, predicted versus residual. If one of those below, then the assumption is not met. Then your model is not valid. This is linear, we don't want this. Quadratic, we don't want this. This funnel-like, again, you don't want this. See, broad variation here, get smaller, smaller, and small. This increasing and coming down, quadratic. This increasing, most likely, is like a share market. The price the next day may depend on the price before. So this is good for time series analysis. In this class, we want this. Otherwise, the model is not valid. The model is not valid. We may want to do some transformation, right? Let's see some example later. What do you want? And residuals must be normally distributed. Again, we've seen many examples, how to test for normality, right? Large sample, more than 300, we just check the skewness and kurtosis. Small samples, we look at the p-value. All right. Then he puts the whole thing into ANOVA, he builds ANOVA table. ANOVA stands for analysis of variance. So look what goes into the variance. This is the source, right? The total, sum square total, this is sum square total for the dependent variable, right? He partitions the sum square total into 2, regression and residual. So what's the regression and residual? So this residual, take all the differences, square, and add them up. So that is a residual. So total minus residual is regression. Sometimes called explained variation. This is called unexplained variation. What's the variation? The differences, how spread the data points are. That's a total. Split into 2. One part is called explained, other part is called unexplained. So what is unexplained variation? It's a summation of the residual square. So this minus this will give you this. I don't go in details. This table will give a p-value. This table will give a p-value for what? Testing whether the slope is 0 or not 0. Right? So look at the residual table, ANOVA table. We look at the p-value here. Right? Just skip. Okay. All right. So here, when the p-value here less than 0.05, then I say y depends on x. The slope is not 0. When the p-value is more than 0.05, then I say y does not depend on x. Follow this. So ask the question, does y depend on x? Put ANOVA table, read the p-value. Is less than 0.05, we say yes. More than 0.05, no. Right? One more term here, r squared. What's r squared? Regression over total. Explain over the total variation. Also called percentage explain variation. Statistics textbook will say coefficient of determination. By understanding this in terms of percentage explain variation better. So this value ranges from 0 to 1 or 0 to 100%. Higher the value, better the model fit. Lower the value, lesser the model fit. So you want whether the model is good or not. Again, all this SPSS click button will give the answers. Question is which table to look for and how to interpret, right? Let me show an example first. Okay, look at the example. So it gives all the values here, summarizes all the value. That's a p-value. Is it less than 0.05?
Yes.
Right? What I'm testing, does BP depend on BMI?
Hmm.
Right? Since the p-value less than 0.05, answer is yes. Right? Later find the other values. What's r squared? Look at the r squared. 790 explain over the total. That's 93.6. So 93.6% of the variation BP is explained by BMI. Right? So that's considered good. Okay, let's do something hands-on. Over here, BMI versus SBP, the same data set. We do this. First is scatter plot. Scatter plot. So follow the yellow dialog box here. Do exactly same. Click OK. You'll get this figure. How to interpret this now? How to interpret this figure?
Still, as the X body mass index increase, the SBP increase. So they have a
positive association. The higher body mass index, the higher the BP, right? So there is an association. Is it strong or weak?
maybe a little bit weak.
We don't know.
We don't know. Have to
Ah.
test it.
It is correlation. So we follow
Right.
instruction, follow this, and click OK. I'll give that value. This is BMI versus BP. This value, 0.669. Is it strong or weak?
It's quite strong.
Quite
I
strong.
mean, about average.
We look at this p-value. Is it less than 0.05?
Yes.
This is p-value, right? So p-value is less than 0.05. So that's a correlation value. Is it more than 0.3?
Yes.
Yes.
I told you here 0.3, right? Right. Is it beyond 0.3 somewhere here, right?
Yes.
Inside here means there's no association. somewhere here. So you say there is a positive association with the two variables. All right. Okay, the higher the BMI, higher the BMI, higher the BP. Okay, different people may want to interpret differently. The doctors may say, oh, this is very high. Some may say this is not very high. It's not like 0.9. But some say 0.6 is considered high. Anyway, more than 0.3. There is an association. So we saw a pattern. We measure strength, quite strong. Less the time you do regression. You follow the pattern, this yellow box here, put the value here, BMI and BP. Here what I want to know, does BP depend on BMI? So this is dependent, this is independent. So run the analysis. We look at the three tables, a few more tables, but let's say we look at three tables first. Follow the numbering. What's number one? What's number one?
P value,
The value. Where? ANOVA table.
ANOVA.
Is it less than 0.05?
Yes.
Yes. What does it mean? BP depends on BMI. Right? What's the next question? I say BP depends on BP. What's the next question? Anis, what's the next question?
What's the equation between BP to SBP to BMI?
No, layman's term.
Oh.
You asked me whether BP depends on BMI or not. You asked me?
Is SBP depends on BMI?
Yes. What's the next question?
How much different?
How? Isn't it?
How does it different?
Right? And is I2, are we two related? Say yes. Are we two
Yes.
related?
Yes.
What's the next question?
How?
How?
Okay.
Right. Does BP depend on BMI? Yes. Next question, how?
How?
Go to the
Okay.
coefficients table and write the equation. About y equals to a plus bx. Number two, write the equation. So as BP, this is a constant, right here. This is a slope, right? So right here, 2.030 times the BMI. So what is the slope? The graph here, we cut here, the slope, that's a value. That's how we say it, as BMI increases, BP increases. How? Every 1 point increase in BMI, BP expected to increase by how many points? 2 point, about 2 units. First question, does BP depend on BMI? Yes. Next question, how? We write the equation. Next step, we explain what this means. Say every unit increase in BMI, BP expected to increase by 2 units. Okay. So does it depend? Yes. How? Number 3, explain. Number 4, how much? Depends, right? How much? Is it 100%? Is it 80%? That's R squared. Just try this. Regression. 12,103 divided by 27,012. Use a calculator, divide. 12.103 divided by 27,012. Somebody divide.
0.448.
Is it the value here?
Correct.
Okay. What is this now? Regression. Explain over the total. 44.8%. That is say 44.8% of variation in BP is explained by BMI. In most social sciences, we need this value. How much does it explain? Right? Higher the value, better it is. But social sciences, very difficult to get so high a value. But whatever there, you report. So the table, click button, all come out. Number one, question is, does this depend on that? P-value less than? Yes. If yes, how? And then what this value means and how much. So follow the sequence 1, 2, 3, 4. You can write in a paragraph. All right, next. Assumptions. Scatter plot. This is age versus, sorry, example 2. This example 2. What's objective here? Example 2. What's
Find
objective?
this between age and
Age and
BMI.
BMI. Age and BMI. So this is scatter plot. So what do you say? Older the age, any pattern BMI?
No.
No pattern, right? This like temperature in New York, rainfall in KL. No pattern. Let's say the strength correlation. Is it big or small? Is this value big or small? Correlation value.
Small.
Small. P value is more than 0.05, right?
Yeah.
Therefore, no significant association. You also can see the R value, this R value is less than 0.3. So scatter plot says there's no pattern. Correlation says there's no association. Let's see what regression says. Regression will give this value, let's say. Is it more than or less than 0.05?
More.
More than 0.05. That means what?
That's
BMI does not depend on age. What's the next question?
how.
Here, BP depends on age. Next question, how? Explain the slope and how much. Now, does BMI depend on age? Answer is
No.
no. What's the next question?
How.
What's the next question?
Regression doesn't explain no relation. Only how many percent?
No. Anis, what's the next question? Anis,
How.
Anis, are we two related? Say no.
No.
No. What's the next question?
No more question after that.
If they are related, then how? Here are they related? No. Then you stop. My question is, are these two related? First example, yes. Then how? How much? But here, are they related? No. You stop. There's no association, nothing to explain.
Right.
Are we clear on this?
Yep.
All right.
Yes.
The next, the assumptions. A video exercise later. Okay, now I will stop here. All right, let's go back. Open a data file. Open the data file. Same file, data set 1, and follow the instructions. First scatter plot, next correlation, next regression. It can be like this, or it can be like this. We don't know yet. Okay, let's do this first, then we do a few exercises. All right. Are you all following?
So now we're doing example 1 or the
Example
one
one.
that you put as the exercise.
No, example 1 first.
Okay, all right.
Right. Okay, what are the steps? What are you supposed to do?
Scatter plot.
Graphs.
Graph, like I say, scatter dot. And click define. Just follow instruction. Your notes. Define here. Y-axis BP. Okay. X-axis BMI. Exactly what's here now. Click OK. Now you see the output. Check the output. All right. Looks like the higher the BMI, higher the BP. Right. Looks like the first way. Next question is strong or weak? We do correlation. Are you following?
Yes.
Right. Correlation. But to analyze, correlate, bivariate. Bivariate. Variables are BMI and SBP. Okay, the two variables here. This is wrong, okay? This chart is wrong. Must follow this. Okay, there's a mistake there. It must be like this.
Okay.
Okay, it must be like this. Continue. Okay. So we'll get the R value. All right, so that's the R value, 0.669. Is this significant? Is it significant? Class, is it
No,
significant?
not significant.
Huh?
No,
Not
it's
significant.
not significant.
Yes. Yes,
Hey,
it
less
is.
than 0.05, right?
Yes.
Yes, significant. Association. Next step. Regression is modeling. I want to get the equation. Right? So go to modeling. So regression. Okay, next step. Regression. Linear. Variable. Now you must be careful which is dependent, which is independent. BP depends on the BMI or BMI depends on BP?
SBP.
As BP depends on,
BMI.
all right.
Yeah.
Time being, that's all. Click OK. Right, 4-point summary. Point number one. Point number one, ANOVA table. P value less than 0.05. Yes, BP depends on BMI. How? So we write the equation. BP equals to 71.028 plus 2.023 times BMI.
So good.
Right.
It's set formula, equations.
So every 1 unit increase in BMI, BP expected to increase by 2 points. How much? 44.8% of the variation in BP is explained by BMI. 4-point summary. Are we clear?
Yeah.
Okay, how do you write this? How do you write this? Again, now I do another example first. Another example first. You do the next one. Age and BMI. Do exactly what I did. Check first. Are you done with this one? What's the conclusion? Eva, what's the conclusion? What's the objective? Age and BMI? No pattern?
Yes, to see the association between the
Age and
BMI.
BMI? So what do you define? Is there a pattern?
No.
No.
In fact, you can stop already. We went ahead, correlation. There's no correlation, no association?
No.
No. Next, regression. P-value more than 0.05. So BMI does not depend on age. Right, a simple write-up. Again, I won't copy and paste all the tables. Just watch which table I'm going to take. So this is, so I'll take only this table. Okay, that's table 1. Again, you just copy and paste like this, I'll fail you. Format the table. Maybe I leave the original table. So you have to format the table according to the whatever format you're following. Right, so remove this first row. We need only this and this part here. So split the cells. So we don't need this. Right. So this is called predictor. And standardized coefficient, T, and the SIG value. So this must follow the same fonts as we have here, font size 11. Hello, Brian. Must Just follow exactly same format. I mean, same font size and everything. So I want the table to look like this. So this will be the AP format. No columns. Right. So as shown, table 1, the value less than 0.001 and SVP equation. I think one figure enough, okay? 71 plus 2 times your BMI. That is. So the R square value was, so I'm not putting all the table inside, okay? The ANOVA table P less than 0.05, it is same in this table. This value here is the same as in this table. Correct or not? These P values are the same. Class,
Yes.
I don't need ANOVA table. I already have the value here.
Okay.
Right. Next, sometimes what they do is copy all the tables and paste it. You do that again, I'll fail you. Okay, it's not the way to do it. You want to put appendix, is fine. You put all this in appendix. But don't put all the table here and mess up. I want to know, that's my objective, how you did it, what method you use, the results in the table, and tell me this is what it means. So what's R square value? 44.8%. Zero 0.448. Which means 44.8% of the variation So they are telling a story. So statistics, nothing else but telling a story. To tell a story, where do you start? Geeta, are you there? Geeta? Geeta,
Yes, Prof.
where do you start? Telling a story, where do you start?
From the objective.
What you wanted to do? What you wanted to do? And how you did it? And how you analyze it? And what's the results you got? And the results, what do they mean? There's a finding, right? Right. So two more to be added. Next is residuals. Residual analysis. I mentioned the notes. There's assumption on the residuals. That must be checked. All right. Assumptions on the residuals. This assumption, independent and normally distributed. So you're going to create this particular chart and see it resembles 1, 2, 3, or 4, and then test whether residuals are normally distributed. And then we conclude our story. Are you ready? Are we ready? Okay, just watch. I continue with where we left off. Regression, linear. Now go to plots. Plots. Always do this only. Predicted and residual. Z predicted in the x-axis, Z residual in the y-axis. We are plotting residual by predicted value. Continue. Save. Save the residuals. Unstandardized residuals. So what's residual? The difference between observed and predicted. So that's your predicted, this is observed, right? So we don't want this, that's enough. Continue. We click OK. Okay, look at the pattern. Is it random? Do the dots look random?
Yes.
Yes. So first assumption is met. Right. So and then we can say analysis the residuals. The independent. Of the random, we say the independent. And what's the next assumption?
People normally.
Distributed normally. So look at the data. Look at the last column. Last column, we save the residuals. Just now I say save. Okay, save residuals. Okay, save for you. So now test whether these residuals are normally distributed. So go to analyze, descriptive, explore. The last variable created, always the last variable, residual one. Plots, normality plot. Continue and click OK. So look at the p-value. What's the p-value here? Is it more than 0.05?
Yes.
Yes. And distributed normally. All right. Conclusion. All right. So we started here. Briefly, how you did it, method, how you analyze it, the results. So what I figure here, you explain. Is it difficult? Jeffrey, is it difficult?
Need some time to digest.
Okay, digest.
Prof, I'm clear on the second last part there before the conclusion. How do we do that to check, to plot the graph there, residual analysis there?
I'll do one more time. Finish first. Finish
Yeah.
right up. I'll do one more time. It's been recorded. You can check again.
Professor,
Yeah.
I don't quite clear about why they have to separate the unstandardized and standardized coefficients.
This one we talk about this when you do multiple linear regression. Okay.
Okay.
Later we'll see that. Have you seen this value somewhere? This value?
Yes.
Where?
Before I show that how good the regression model is.
It's actually R value, right? This is actually the
Yeah.
R value, right?
Yeah, value.
Right. We talk more about this later, okay? Why is it important? For one variable. Why is it called simple linear? Simple linear. Why is it called simple?
Only one.
Only X and Y.
Only one independent variable. If they're simple, there must be. If they're
One.
simple, there must be.
One relations.
If they're simple, there must be multiple, right?
Yes.
If they're
Multiple.
simple, there must be multiple, right?
Yeah.
Yes.
What matters is only this, not so much this. But to go to multiple, you must understand the simple first. From next week, it's going to be multiple all the way. The things don't depend one at a time. That's called simple. One predictor. Later multiple, there will be more than one predictor. Example, maybe one more variable may come in. One more variable. Let's say age comes in. Possible? It's simple or multiple?
Multiple.
Anything more than one is multiple. So in a PhD, all these are useless. Then why are you doing this?
Understand the basic.
I have to understand basics. So when you go and put all these values, some other values here, you know what these values mean, how to interpret this, right? So that will be multiple. So that's what required for PhD, not all this. Okay, now what does it mean? What are you asking? Does BP depend on BMI and age, right?
Yeah.
So what is your conclusion? Does it depend on BMI?
Yes.
Yes. Does it depend on age?
No.
No.
Friends.
It depends only on BMI. So this alone is not enough. That explains only 44%, right?
Yeah.
When you add more variable, this will increase. The better understanding, right? Better explanation. So that's what will come next week. Before that, you must practice this and make sure you understand what exactly you're doing. Okay. I'll show you one more time how to get these values. Remove this. So analyze, regression, linear. Let me reset, go again. Aini, right? Not Aini. Anis, you count the number of clicks, okay? Ready? Anis, are you there? No. Gita, are you there?
Yes, Prof.
Okay, count, okay?
1, 2, 3, 4.
Let's not count it, huh? It's a mistake, okay?
Oh, 5.
It's all right?
Yeah.
How many clicks?
5.
How long it took?
Less
10
than
seconds?
10 seconds.
You know how long would have taken those days to calculate all this? No calculator, manually? All right. So you are very fortunate, right? So only this table. Copy and paste this table and explain. Jeffrey, are you okay? Jeffrey?
Yes, yes, yes. Thank you, Prof.
Now look at the plots. We get into this now, right? The plot. That's it. Okay, these two. Oh, sorry, I entered the wrong one. This must be plots. This is must be a mistake, right? Residual.
Professor,
Yeah.
I don't understand why the X and Y are a ZP.
Okay.
What that means?
This is predicted on the line. This is residual. You look at my notes. In my notes, right? This is a residual of my chair. This is a predicted. I'm going to plot predicted versus residual. But
Okay.
here, we are taking the standardized. So plotting. This is residual, receipt. And this is predicted. Is predicted. So predicted here. Yes.
Yeah, I get that. Thank you.
Continue and click OK. So now we can see this graph, the dots are called random. What's not random is the dots are going up like that, or going up and coming down, or very wide here, get narrow, 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 narrow. The first assumption is met. Second assumption is normality. already asked SPSS to say for me. Right. Always take the last one. That's default, doesn't matter, the last one. Plots normality. We've done this many times. That's a p-value. So we conclude they are independent and distributed normal. So this model is valid. Unfortunately, this explains only 44%. Next we'll see how to increase, how do you increase number of variables and see how this changes. Are we clear? Class, are you clear?
Professor,
Right.
how can you get the 44.8%?
4%. So you see the tables, right? Let's say 1, 2, 3, 4, isn't it? This 1, this is 2, this is 3, that's 4. R square, right? This R square, isn't it?
Oh, yeah, I see.
Right. So the 3 tables. So that's R square, 44, 0.448, which means 44.8%. So objective, method, analysis, results, residual analysis, and finally conclusion. So we're not happy with the model because the only 44% explained. There are more variables out there which are not accounted for.
So the residual analysis is not in the conclusion.
Now we don't know. We don't have that. Our objective is only this, right? Isn't it?
Yeah.
If my objective is BMI. It depends on what, right? Objective clearly BMI, age, right?
Yeah.
Then will be multiple. You see, my objective is only BMI. Therefore, analysis is simple. One variable. If my objective is more than one variable, BMI and age, let's say, then would be multiple. BMI, age, and BP. That will be multiple. As always, writing the objective clearly is very, very important. As I the first day I told you, go and download the abstract. Most of the time they mention what was the objective. That means what they want to do. Then you know what method they used. Clear? Who asked the question? Are you clear?
Yeah.
Right. So now, your time. Go into the exercises. All right. Okay, do one first. Number one first. DBP and you do the analysis for number one. Okay. For number one, do the analysis, write the report, and email. Are we clear? Class, are you clear?
Yes.
Yes.
For this, do the whole thing, write up, email. So your subject must be, is it assignment? Exercise on simple linear regression. So this is
So just the first one is right, DBP and the BMI, right?
this one.
Okay.
Okay, only that. So as you practice, you know what table goes in and how to do the simple write-up. Again, I told you, it's still useless because you have to do multiple. Multiple, just going to expand it more than 2 variables. Same like t-test, 2 levels, we expand it to ANOVA. So the same thing, simple linear, 1 variable, later going to increase the number of variables. All right, so do this, submit. I'll give you 15 minutes. 15 minutes, 5:20. We start, we continue at 15 minutes, 5:25. 5:25.
Send to you, is that correct?
Say again. Say again.
After we're going to do this exercise and then send to your email. Is that correct?
Yes, correct. Okay, I give 5:30.
Okay.
Okay, 5:30. Okay, send me
Okay.
before 5:30. We continue at 5:30.
Sir, where can we get the data set?
Hey, data given to you, data set 1 from the first class.
Oh, okay, it's the same. Okay, okay.
Got it?
Yeah, okay.
That data set is very important. Okay, you're going to continue using the same data set next week. So you know how much wealth.
Original one, you change the data set.
Data set 1?
Yeah, last week you sent us a new data set.
That's different. That's why I said
So we use the original one.
original data set 1. I already put there, file data set 1.
Okay.
Look at the slide. Data set 1. Okay?
Yes, for
Since you have to practice, shall I give one more? Yes, since you have practice, you have to practice. I'll give one more. Since you're doing one, you can do one more, right? Eva can do one more, right? Eva? Is that
and
a-
raw.
huh?
Can.
Can do, right? Okay, since nobody said anything, so I feel general consensus that you can do one more. All right. How many pages? How many pages? 2. Only 2 pages, okay? 1 page on this, another page in second example. 2 pages only. Try to write as briefly as possible. I'll come back at 5:30.